So today I'm going to introduce some of the very recent results we had on the theory of multi-agent reinforcement learning. And I'm going to present you some positive results or negative results, depending on how you interpret those. So let's get started. Right. So since this is the first, I think, talk about this topic, in case you have any questions, feel free to interrupt me anytime. Okay. So as we all know that with the expanding reach of reinforcement learning in many real-world applications, we often have to deal with systems that involve a large number of agents. And these agents could be competitive or cooperative agents, leading to very different dynamics. And in the cooperative settings, agents are allowed to coordinate and communicate with each other in order to achieve a shared common goal. And this is closely related to the distributed optimization, and there has been a lot of recent success in this line of work. In the competitive setting, oftentimes agents learn policies that are self-interested in order to maximize its individual rewards. And this is what we're going to focus on today. And in the competitive setting, unlike the cooperative settings, the goal here is really seeking to compute some kind of equilibrium. And I should mention that there has been significant progress in the past years on structured game settings, such as zero-sum Markov games, Markov potential games, and many other settings. I think many of the audience here, like Kostis, Noah, Simon, they have contributed significantly to the literature there. Okay? So in this talk, I'm going to focus on the many agent setting, which is the case where in the system, the number of agents that are involved is huge. And here I'm not going to make any sort of structural assumptions like zero-sum or potential structure here. I know that many of us do not really care about applications, but I do want to point out that applications involving many interacting decision makers are essentially everywhere and span a wide range of applications, right? This includes, say, for example, in social science, where we try to model social dynamics, online bidding behaviors, or in engineering applications like traffic control, in smart grid, or resource allocation, as well as in many scientific applications like the modeling of brain activities or the modeling of like animal herding effects, so on and so forth. And as you can see that in many of these applications, the number of agents or decision makers involved are huge. Okay. So in general, we know that, of course, many agent reinforcement learning is known to be notoriously hard to solve. And the hardness comes from several curses. Right? The first curse is due to multi-agency, as we know that the size of the state action space scales exponentially with the number of agents. And this means that the requirement on memory and also on computation can be prohibitively expensive. And the second curse comes from the tractability, and this is already shown that even without state dynamics, right, in the standard normal form games, already computing, say, for example, Nash equilibrium for general sum games is PPAD complete, and this is largely due to Kostis and co-authors. And PPAD complete is known or is conjectured to have no polynomial time algorithms. Okay? And lastly, recently has also been shown by Dylan and Loa and Sham that if we are going to let agents to play independently while some no-regret learning algorithms, then it is already computationally tractable, even for computing some weak notion of equilibrium, like coarsely correlated equilibrium, and this holds true even for very simple, say, three-player Markov games. Right? At this point, this seems to be like a hopeless problem to solve, and we all know that if we are encountering some very hard problem, what should we do, right? Either we just change the problem, which of course is not what we really want to do here, or we can really relax the solution concept here. And this is precisely what I'm going to show you here in this talk, is that we're able to break all these curses through the so-called mean field gain approximation. So let me first maybe just formally describe for the n-agent reinforcement learning problem here, right? Each agent's I has its own state transition dynamics Pi and also its own reward function Ri. And these state dynamics and also reward functions depend on all the state and action informations among all agents in the system. Okay? And we know that if all these agents' dynamics and rewards are symmetric, in the sense that, right, these are the same for all agents, and if the number of agents in the system n goes to infinity, and then we can actually obtain an abstract simplification of the so-called mean field games. Right? In the mean field games, all the individual interactions now can be replaced simply by the interaction between a representative agent and the population, or the so-called mean field. Okay? So more specifically, for a given representative agent, right, the dynamics, the state transition dynamics, and the reward now will only depend not only on the current state and actions, but on the aggregated information of the whole population, right, which is through this population state action distribution, okay, which I'm going to denote this as mu here. Of course, we know that in practice, oftentimes, right, n is not necessarily going to infinity, and agents may not necessarily be identical or symmetric, right? We've shown that actually, even for a finite number of agents n, and even for heterogeneous agents, we can actually always construct some mean field gain approximation, which I will first maybe go through some of the mathematical description of these two problems and what are the solution concepts related, and then I'll show you what is the construction there. So let's start with the n-player dynamic games. Right here, we have n agents, and we consider the finite horizon setting where the length of horizon is h. And we look at finite state action sets here. And I should mention that many of these definitions and results analysis can be extended to also the infinite horizon discounted settings, which is usually known as the stationary mean field games or stationary games. And I will make some distinction later on as we go along. So in the n-player dynamic games here, we're going to denote rho as all the state action configurations among our agents, and the dynamics for each agent I basically follows, right, the state, the next state follows the agent I's state dynamics pi, right, which depends all the other agents' state and action pairs, and agent I is going to take some Markov policies, which depends on the current horizon h. And the reward, again, is going to depend on all the state and action among all agents there. Right? Since each agent has its own reward function, its own objective to maximize, right? A natural solution concept here is the so-called Nash equilibrium. And here, by Nash equilibrium, we say that no agent has any incentive to deviate from the current strategy or policy. In other words, no agent can really exploit over others by single-handedly deviating from its own current policy. So particularly, we're going to define the exploitability as the difference in the value functions between the current policy pi star and the best response that agent I can take, right? We're going to call this difference the exploitability for agent I, and we're going to take the maximum over all agents I from 1 to n, and this is called the exploitability of this joint policy pi star, okay? And if the exploitability is less than or equal to epsilon, we call this policy pi star is epsilon Nash equilibrium policy. As you can see that when epsilon goes to 0, this basically reduces to the Nash equilibrium. Okay? And I just want to point out here, right, these value functions for the finite horizon setting is defined by the aggregated rewards over the finite horizon of length h. And in the infinite horizon case, then we'll consider some discounted factor there. So this is the standard n-player dynamic games. So if, as I said, yes? So here we consider Markov policy because, first of all, we don't want to consider stationary policy, right? We wanted the policy to be dependent on h, and then it only depends on current state observation for agent I. Mm-hmm. History, okay. It should make things more complicated, yeah. But here, for simplicity, we're going to look at Markov policy, and this is already the case where if we just assume, say, Lipschitz continuity of your transition dynamics P and R, then this Nash equilibrium defined by the Markov policy here is already exists. Right. So existence is guaranteed by very minimal assumptions like Lipschitz continuity of P and R in terms of dependence on. Right. So as I said, if the number of agents goes to infinity, right, if all agents are basically follow the same state transition dynamics and the rewards, and this is leads to the so-called mean field games. And this is kind of the infinite agent settings, where again I look at the horizon H, and at every time H, right, we can define what is the population distribution, which is basically the distribution over all the state and action that's taken by all the agents. Okay, and then the state transition dynamics looks as the following, right? The next state is going to follow from this transition P, which is the same among all agents. That depends on the current population distribution mu H. Similarly for the reward. Okay. And similarly, we can define the policy to be the equilibrium for these mean field games if this policy is optimal or is the best response with respect to the mean field. Basically, if all the agents in the system are following some policy pi star, then no single agent can improve its own policy by deviating from this policy pi star. Okay, so this is sort of the natural definition of mean field gain equilibrium here. Okay, and just maybe as a notation here, for any given policy pi, right, this induces what is population evolution under this policy pi, right? That's what I denote as mu pi. Okay. So in the stationary mean field game settings where we consider stationary policies, oftentimes it's assumed that the mean field or the population remain fixed throughout. Okay, and the definition of equilibrium is slightly different there. Yes. It can be randomized, yeah. Yes, right. Cool. So of course, as I said, in practice, oftentimes n is not necessarily going to be infinity, right? Agents may not be exactly symmetric to each other. And we've shown that, in fact, for any arbitrary n-agent reinforcement learning problem, we can actually always extract, or we can always construct some mean field gain approximation by just taking some symmetrization operations and also smoothly extending this to the infinite player continuum with some Lipschitz extension. Okay? And here's basically what this construction looks like. Suppose we're given some n-player dynamic games where the transition dynamics and rewards are different. So we can actually define some transition probability P by just taking the averaging, by first of all taking symmetrization of each of these agent i's transition dynamic P, and then extend this into the probability space and averaging out over all agents n. Okay, we do the same thing for the reward function. Here the symmetrization is basically just averaging out all possible permutations of the state action pairs among all agents to make it a symmetric function. Okay? And the Lipschitz extension here is just to say that if this function is defined on some empirical distribution, then we can actually easily extend it to the entire simplex set. So this is just a definition. Later we'll not even use all these abstract mean field games here. It's just used more in the analysis. So basically now we have shown that we are able to construct some mean field gain approximation for any arbitrary n-agent reinforcement learning problem, right? Then immediately there are three questions we want to answer here. First of all, how good does this mean field gain approximation how good does this mean field gain approximate the n-agent reinforcement learning problem? Secondly, right, how easy it is to solve this mean field gain problem, right? What are the statistic and computational complexities of solving these mean field gains? And lastly, and also more practically, we wanted to ask also, can n-agents directly solve this problem to achieve some desired equilibrium by learning independently? Okay. And in the next 15 minutes or so, I'll try to give you some brief answers to each one of them. So first thing first, how good is this mean field gain approximation to the n-agent gain here? So of course, a natural definition of goodness here is we can just directly use this exploitability here, right? Suppose we're able to compute the equilibrium of the mean field games, and we let n agents all follow the same policy pi star here, and we want to see how large is this exploitability, right? If the exploitability is already small, then that basically means this is approximately good natural equilibrium to solve the original n-player game problem. And this problem actually has been studied in several existing work, and this work only provide asymptotic rates showing that if n goes to infinity, then this exploitability will go to 0. And many of these existing results only considered also the stationary setting rather than the finite horizon setting. And this includes, say, for example, the exact symmetry case where agents are homogeneous. This has been developed by this few work. And there are some extensions to the case where we have multiple type of population in the system, and we can group agents into different populations. And recently, there are also some, I think, generalization to the Garfunkel games where agents are independently drawn from some distribution. Okay. In all this existing work, they only consider asymptotic results that when n goes to infinity, it will converge, like the mean field games or the n-player game will converge to a mean field game. And our focus here is we wanted to consider the case when the number of agents n is finite, right? Horizon h is also finite, and we're going to deal with also heterogeneous agents. So let me just show you one of our key results here on the approximation guarantees, right? If we're going to define pi star as the mean field gain equilibrium of the induced mean field games that we constructed earlier, and then we can show that if we consider this policy where all agents follow the same policy pi star, and the exploitability of this policy will then be bounded by these three terms here. And let me just unpack it for you. So the first term here corresponds to the approximation error due to the fact that we only have finite number of agents here, right? As you can see that this term scales in the order of 1 over square root of n, right? As n goes to infinity, this term will diminish to 0. Of course, you can also notice that it has a very unpleasant dependence in terms of horizon h, right? This is, in fact, exponentially sensitive to h, right? In the case where, I should also mention this parameter L here is a Lipschitz constant of the population evolution operator, right? This is how, right, at a given population mu, if all agents play policy pi, how the population will evolve at the next round. Right? And L is the Lipschitz constant here. If the underlying, say, dynamics is relatively stable, then oftentimes this corresponds to a Lipschitz constant that's smaller than or equal to 1. And then you see that this term actually would then only have polynomial dependence on H. In the case when L is arbitrarily close to 1, or when this operator is non-expansive, right, this will give you like a cubic dependence on H. Okay. So this is the first term here. So the second term actually corresponds to the approximation error due to the dynamic heterogeneity among the agents. And particularly this constant alpha here characterizes what is the dynamic heterogeneity, the degree of dynamic heterogeneity. And this is defined as the maximum L1 norm discrepancy between individual state dynamics PI and the constructed mean field dynamic P. Okay. So if agents are all symmetric, then this alpha is equal to 0. Okay? And if they're roughly symmetric, then this alpha will be small. Okay? As you can see that this term also has the same sensitivity or the same dependence on H and L, right? Similarly as this term here. Okay? The third term corresponds to the the approximation error due to the reward heterogeneity, and beta corresponds to the degree of this reward heterogeneity, which is defined similarly, except we're looking at the L1 distance, the distance between Ri and R. Okay. And this has a much milder dependence in terms of the finite horizon H. Yes? Why we have better upper bound? Right, here. Right, so the more agents we have, then we are more closer to the mean field regime, right? That's why you see that this actually scales in the order of 1 over, right? So what's of course interesting here is that as we just pointed out, right, the more agents we have, then the tighter this approximation error will be. And the sort of the takeaway here is that the mean field game approximation is good proxy for the n-agent game problem if the underlying dynamics is relatively stable, and also it is quite robust to small violations of symmetry. Okay? And let me just point out in the very special case when there is exact symmetry, when alpha and beta equal to 0. In fact, this non-symptotic result is also the first in the literature that we've shown that we have this indeed exponential dependence on h, right, in the worst case. Exponential dependence on h in the upper bound. And we actually shown that also this is the case in the lower bound. We can actually construct some hard instance where we cannot really get rid of this exponential dependence on h. So this is basically unimprovable in the worst case. Of course, for those of you who are interested more in the infinite horizon stationary settings, we can show that similarly, if the population evolution operator is non-expansive, then we can show some approximation upper bound, which scales cubically in the effective horizon, which is kind of aligned with the final horizon setting. And if we don't have any of these non-expansiveness assumption, then this exploitability can, in the worst case, can be super, super slow, right? This will converge very slowly in terms of as n goes to infinity. Yes? Right. We'll use the same policy, yeah. So here, of course, for the original game, right, the optimal Nash equilibrium does not necessarily have to take the same policies. Here we say that if they take the same policies, it's not going to be too bad, right? Yeah. Yeah. Right. There is this, basically it's guaranteed by this bound here. Okay. Yes. 5 minutes. Okay. Cool. All right. So now we're going to also answer the second question, right? How tractable it is to solve these mean field games. And let me just speed up a bit. So first of all, we want to look at the computational tractability, right? Assume that we know the underlying mean field game models, right? How hard it is to solve this mean field game problem. In fact, this has been studied in several existing literature, and many of this existing literature needs to impose some structural assumptions. So for example, if in the stationary mean field games, if we assume the underlying population evolution operator is contractive, then we can show that solving these mean field games only reduces to basically solving logarithmic 1 over epsilon number of single agent RL. And in the finite horizon setting, and if the reward is monotone and the dynamics P has no dependence on the population, then this also can be efficiently solved by just reducing to 1 over epsilon 2 number of policy evaluation steps. So we provide a bit negative results here, showing that if you remove all these structural assumptions like monotonicity or contractivity, then in general, if you just assume minimal assumptions, just like Lipschitz continuity of P and R, then this problem is indeed PPAD complete. So sort of this says that to solve these mean field games efficiently, it seems to be unavoidable that we have to impose some structural assumptions there. Okay? And let's put computation aside and see is it statistically tractable to learn these mean field games if we don't know the model. Okay? And we want to understand, say, for example, if we're given a hypothesis class about the underlying model, how many samples are efficient to sufficient to learn the Nash equilibrium. Of course, this topic has been extensively studied, right, by this particular community about what has a sample complexity in the single agent reinforcement learning setting. And if we move from single agent reinforcement learning to the mean field game setting, naturally one would expect that its exploration will be even more challenging because the transition dynamics and the reward now depends also on the population, which is infinite dimensional. Okay? Surprisingly, we've shown that actually exploring these mean field games is not that hard compared to single agent reinforcement learning. And here's one of our recent results with my student Java and my colleague Andres Krause, where we've shown that if you're given a model class M, and if we assume realizability, that the true model M star stays in this model M, and we assume, again, the minimum assumption that the P and R are Lipschitz continuous in mu, then we can actually construct some iterative model elimination-based algorithms based on these optimistic MLE type of methods that would require only the sample complexity of order polynomial in terms of some intrinsic dimension of the underlying model class, and the polynomial in horizon H, and as well as many other problem-specific parameters like the Lipschitz constants, etc. Okay, and this intrinsic dimension here is just more like a generalization or a new notion of model-based eluder dimension that is tailored for the mean field gain settings. And we prove that this parameter or this dimension here is indeed small for many interesting cases. For example, in the tabular setting, for tabular mean field games, then this eluder dimension is indeed less than equal to state S times A, similarly as in the single agent reinforcement learning setting. In the linear mean field game settings, if the transition dynamics follow this factorization here, where this phi feature vector phi is known, then we've shown that this dimension is also less than equal to the underlying feature dimension D there. Okay. And we also had many other instances, like extending this to the kernel mean field games or generalized linear mean field games, and shown that in many cases, right, this underlying dimension here can be very small. And as you can see that in the special case, when LP and LR is equal to 0, this basically means that your reward and your transition P has no dependence on the population. Then this basically reduces to the single agent reinforcement learning. And this is more or less aligned with what we already observed in the single agent reinforcement learning setting. Okay. What's interesting or to note here is that, as you can see, that this whole complexity here has no dependence on N. Right, so this is exactly what actually breaks the whole curse of multi-agency. And I should point out that there are existing work that looked at also convergence to, say, for example, closely correlated equilibrium of multi-agent systems. And oftentimes there, the dependence, the complexity oftentimes depends on the number of agents. But here, the complexity has no dependence on the number of agents in the system. Okay. So now we move on to the very last question that we would like to address is, in practice, of course, we don't really want to implement mean field games because this requires simulating infinite number of agents, and it requires to track the underlying population, which we don't want to do that, and it cannot be done efficiently. So the idea is, can we just directly leverage an agent simulator and directly let agents to run independently some policy gradient type of methods in order to achieve the desired equilibrium? So again, like many of the existing work looked at mean field games, oftentimes require infinite agent simulations. Here we've shown that, in fact, if you just apply, say, policy gradient type of methods, right, for every agent, if you keep the policy fixed, and then you can just sample some state action transitions to estimate the underlying Q values through TD learning algorithms, and then you just plug it into the policy mirror descent or policy mirror ascent algorithm, and then just run this policy mirror ascent algorithm for every agent independently using their own estimated Q value functions, then this will already get the job done. Okay. So maybe just to give you a very informal statement here, that if we let n agents run independently policy mirror descent algorithm, then the overall sample complexity required is only polynomial in 1 over epsilon, up to some approximation error in order to converge to some epsilon close to the equilibrium. Okay. And the caveat here is that, of course, we're not able to be arbitrarily close to the original equilibrium, right? So we always have to subject to some approximation bias due to the symmetrization bias, and also the fact that we only have n agents in the system. And we provided the theoretical guarantees for a number of mean field game settings, like stationary mean field game settings with regularization or finite horizon mean field games. These all require some slight modifications of the choice of the regularization we see earlier in the mirror descent algorithm, and different choice of step size is needed for these different mean-field game settings. And what I would like to note here is that the abstraction of these mean-field games is used only in the analysis, right? We're not really using it in any of these algorithms. Okay, I'll skip these. And let me just come back to where we started with, right? These recursives of many agent reinforcement learning. And I hope I have convinced you that, in fact, maybe mean-field games is a promising, a viable solution to address at least many agent reinforcement learning approximately, right? It provides good approximation under very reasonable assumptions with mild asymmetry. It is computationally and statistically tractable with additional structural assumptions. And it can be solved with independent learning using policy gradient type of methods. And of course, there are many, as I said, this is more like the means rather than the ends, right? There are potentially many other different ways that we can approximate mean-field games. And there are also many, many open questions here left unsolved, right? For example, can we address these computational and statistic gaps here, as we see in some of these results? And also, can we go beyond this benign asymmetry and consider more generic heterogeneity assumptions? And can we construct other alternative approximations rather than mean-field games to address many agent reinforcement learning problems? With that, I just want to point out that there are many other results in these papers that I did not really have time to cover in this talk, but feel free to, check them out or ask me offline. Yeah. All right. Thank you. Yes. What is the assumption there? Right. Right. What is the difference between, yeah. Right, so the difference is, as I said, so here this is on the computational side, and for the independent learning I had in the last, let me just point out to here, as I said, this is a very informal statement. So we needed to consider more structured settings in order to really get this work, right? Particularly these results holds for, say, for example, stationary mean-field game settings where you add regularization that guarantees that you have contractibility and then it's solvable, or in the finite horizon settings where we needed to add monotonicity of the rewards in order to get these bounds here. Because the problem is hard, right? And yeah, we need these additional assumptions in order to get independent learning to work. Thanks for pointing that out. Yeah. Yes. Mm-hmm. It's possible that this 1 over square root of n can be improved by considering different policies for different agents. Yes. We don't have a lower bound in terms of dependence on n here, but I think that's possible. Yeah. But I think there are also results showing that if you only apply this the same policy for every agent, then asymptotically you will only get 1 over square root of n. But if you consider different policies, I think that's a whole different story. All right, cool. Thank you.